It's Iggy X. They got one more problem with you, girl. Hey.
Today we're going to be working on question 1 from 1985 College Board Free Response. At 25 degrees Celsius, the solubility product constant, KSP, for strontium sulfate, SrSO4, is 7.6 times 10 to the negative 7. The solubility product constant for strontium fluoride, SrF2, is 7.9 times 10 to the negative 10. Part A. What is the molar solubility of SrSO4 in pure water at 25 degrees Celsius? So since this is a solubility problem, it's always good to start out with a full equation. So we have SrSO4 solid yields Sr plus 2 ion, which is aqueous, and then SO4 negative 2 ion, which is also aqueous. Now we can set up an ice chart. And since SrSO4 is a solid, we can omit it from the equation. And since these two are products, they start at 0. And we don't know the concentration of them, so we're just going to call it X. And we can add X to each of them, and we get X and X. The next step is to write a KSP equation. And KSP, as we know, is products over reactants. But since the reactant is a solid, we can just omit it and do the concentration of the products. So we'll have concentration of Sr plus 2 times the concentration of SO4 negative 2. In the problem, when you read it, we can see that KSP equals 7.6 times 10 to the negative 7. And then we're going to substitute these in for X. So we have X times X. So 7.6 times 10 to the negative 7th equals X squared. Now to solve, we take the square root of both sides, and we get X equals 8.7 times 10 to the negative 4th molar. And that's your final answer for part A. Part B. What is the molar solubility of SrF2 in pure water at 25 degrees Celsius? So this is basically the same thing as question A. So we're going to start with a full equation. So we have SrF2 solid yields Sr plus 2 ion aqueous plus 2 F negative aqueous. Make sure you balance the equation because this 2 is going to be important later on in the problem. So now we can proceed to make an ice chart. SrF2 is a solid, so we once again can omit it. And then these are products, so they start with 0. We're just going to call this one X. But since this one has a coefficient of 2, it needs to be 2x. So we're going to add 2x there. And we're going to get x and 2x. Now write your KSP equation, which is products over reactants. But the reactants is solid, so we omit it. So we have KSP equals concentration of Sr plus 2 times the concentration of 2 F negative, because we have a 2 coefficient here. And we also have to square this because of the coefficient. Now when we read the problem again, we see that KSP equals 7.9 times 10 to the negative 10 equals, we plug in X for Sr plus 2, and then we plug in the 2X for the 2F minus, and don't forget to square it. So now we have 7.9 times 10 to the negative 10 equals 4x cubed. Next step is to divide both sides by 4 to get 1.975 times 10 to the negative 10 equals x cubed. So now we take the cube root of both sides to get a final answer of x equals 5.8 times 10 to the negative 4th molar. That's your final answer for part B. Part C. An aqueous solution of SrNO32 is added slowly to 1 liter of a well-stirred solution containing 0.020 moles of F minus and 0.10 moles of SO4 negative 2 at 25 degrees Celsius. You may assume that the added SrNO32 solution does not materially affect the total volume of the system. Which cell precipitates first? And what is the concentration of strontium ion, Sr plus 2, in the solution when the first precipitate begins to form? So in order to do this problem, we will have to find the molar concentration of Sr plus 2 in both SrSO4 and SrF2. So to start, we know that KSP equals concentration of Sr plus 2 times the concentration of F minus squared. And this also equals 7.9 times 10 to the negative 10, which we found out in the beginning of the problem. And since it tells us that the concentration of F minus is 0.02, we can plug that in, and we can plug X in for the concentration of S plus 2, because this is what we are solving for. So now we have X times 0.02, don't forget the squared, equals 7.9 times 10 to the negative 10. Now we have 0.0004x equals 7.9 times 10 to the negative 10. So to solve, we divide by 0.0004 on both sides, and we get x equals 1.98 times 10 to the negative 6 molar. Now we have to also do the same thing for SrSO4. So we have KSP equals the concentration of Sr plus 2 times the concentration of SO4 negative 2. And we know that this equals 7.6 times 10 to the negative 7. We can now plug in X for the concentration of Sr plus 2 because we don't know what that is, and we can plug in 0.1 for the concentration of sulfate and solve because it gets us that in the problem. So we have X times 0.01, not 0.01, 0.1 for the concentration of sulfate equals 7.6 times 10 to the negative 7. So we divide both sides by 0.1, and we get X equals 7.6 times 10 to the negative 6. Now the question asks us which salt precipitates first, and when we compare both of these numbers, we can see that SrF2 will precipitate first because it has a smaller value for the concentration of Sr plus 2, which is 1.98 times 10 to the 6 molar. So this is going to be the concentration of the strontium ion, and this is the SrF2 is going to precipitate first. Part D. As more SrNO32 is added to the mixture in C, a second precipitate begins to form. At that stage, what percent of the anion of the first precipitate remains in solution? So first off, we know that the second precipitate to form is SrSO4, which appears when the concentration of Sr plus 2 is 7.6 times 10 to the negative 6 molar. So once again, we will write a KSP expression. So KSP equals concentration of Sr plus 2 times concentration of F minus squared equals 7.9 times 10 to the negative 10. Now, since we know that SrSO4 forms when the concentration of Sr plus 2 is 7.6 times 10 to the negative 6, we can plug that into the expression. So we get concentration of 7.6 times 10 to the negative 6, and then we can plug in X for the concentration of F minus because we don't know what that is yet, squared, equals 7.9 times 10 to the negative 10. Now we can solve. So we can divide by 7.6 times 10 to the negative 6 and get X squared equals 1.04 times 10 to the negative 4th. Now we take the square root of both sides and we get X equals 1.02 times 10 to the negative 2 molar. However, this is not our final answer because it asks us what percent of the anion precipitate remains. So at this stage, the percent of the anion, which is F minus, of the first precipitate that remains in the solution will be equal to it will be equal to 1.02 times 10 to the negative 2 molar, which we get from here. And then we're going to put it over 1.98 times 10 to the negative 2 molar, which we get from the previous parts of the problem. Multiply that by 100, and we get a percent of about 50%. And this number, it comes from the calculated molarity of the Sr plus 2 calculated in Part C. So this is your final answer for Part D of question run.
I got one last